Hi everybody, Mrs. Pesic here.
And Miss Bella here.
And we are now looking at section 7.2, Theoretical and Experimental Probability. Your objectives here are to find the theoretical probability of an event and find the experimental probability of an event. And look at all this new vocabulary for you, including sample space, complement, favorable outcomes, and more. So the probability is the measure of how likely an event is to occur. Each possible result of a probability experiment or situation is called an outcome. The sample space is the set of all possible outcomes. An event is an outcome or a set of outcomes. So, for example, if the experiment is rolling a number cube, the sample space would be 1, 2, 3, 4, 5, and 6. And if we were spinning this spinner as our experiment, our sample space would be red, blue, green, and yellow.
Whenever we talk about probabilities, they're going to be written as a fraction or decimal from 1 to 0 or percents from 0% to 100%. So if we're taking a look at this little scale here, again, impossible would be that it's at 0 or 0%. Certain will be at 1 or 100%. So as likely as not, so about 50-50 chance, you see right in the middle is 0.5 or a fraction of a half or 50%. So the closer you get to red, the more certain it is to happen, vice versa with the blue. So equally likely outcomes have the same chance of occurring. So when you toss a fair coin, heads and tails are equally likely outcomes. Favorable outcomes are outcomes in a specified event. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes to the number of total outcomes. So again, let's look at this definition. Maybe we can talk about an example here. Again, the probability of an event happening is the number of favorable outcomes over the number of outcomes in the sample space. So I'm just going to go back to that one on this first page for a second, where we talked about rolling a number cube, and your sample space was 1 through 6. So if I want to know what's the probability of rolling a 2, okay, so probability of rolling a 2, well, the favorable outcomes, you can only get a 2 one time if it lands on the side with the 2. So there's only one option for that to happen. And how many are there possible? There are 6 options of what could happen. So its probability is 1/6 that that would happen. So that's what we mean when we say theoretical probability. You know exactly how many times something can happen and how many it is going to happen in this case. So let's try an example here. So we have each letter of the word probable is written on a separate card. The cards are placed face down and mixed up. What is the probability that a randomly selected card has a consonant? So a little English here also. We need to know what is a consonant. So P, R, B, B, L. All of those are consonants. So that's going to be 1, 2, 3, 4, 5 consonants or 5 favorable outcomes possible. The total number are how many letters we have altogether. So if we add in the other 3 vowels we have there, there should be 8 possibles. So our probability of having a consonant is going to be 5/8 or 5/8. It would be 5/8. Okay, let's try our second one here.
Okay, for this example, we are going to take 2 number cubes and roll them. What is the probability that the difference between the 2 numbers is equal to 4? So we've got these 2 number cubes, and if the difference is going to be 4, well, that might occur when the red is 5 and the blue is 1, or when they're 6 and 2, or when it goes the other way, when it's 1 and 5 and 2 and 6. So it looks to me like there's only 4 different ways to get the number cubes to have a difference of 4 out of how many possible combinations are there altogether. Well, if you add up all of the numbers here, that is 36 different combinations. So 4/36, and we could even reduce that and say that the number 4 favorable out of 36 reduces to 1/9. So the probability of rolling 2 number cubes so that their difference is equal to 4 is going to be 1/9. That brings up a notes must do for you. A red number cube and a blue number cube are rolled. If all numbers are equally likely, what is the probability of this event? That the sum is going to equal 6. So check out these 36 different combinations and find out how many of them have a sum of 6? All right, so the sum of all the probabilities in a sample space is equal to 1. A complement of an event E is the set of all the outcomes in the sample space that are not in E. So going back to this for a second, this example that we did together here, if the probability of rolling 2 number cubes so that the difference between the 2 numbers is 4, we could say what's the probability of rolling 2 numbers so that the difference is not equal to 4? And that's going to be 1 minus 1/9, because it's 1 minus the probability that the difference will be 4, and that would give us 8/9. And that is shown here in this definition of complement. The probability of the complement of an event E is the probability that something is not E is going to be 1 minus the probability that it is E. And so let's take a look at this example. In this application, there are 25 students in a study hall. The table shows the number of students who are studying a foreign language. What is the probability that a randomly selected student is not studying a foreign language? Well, the probability that they're studying a foreign language, the probability they're not studying a foreign language is going to be 1 minus the probability that they are studying a foreign language. So we want 1 minus the probability that they are studying a foreign language. So let's count up how many students are studying a foreign language. We've got 6 plus 12 plus 3, that is 21 students. So really the probability that that a student randomly selected is studying a foreign language is going to be 21 out of, and they told us the total was 25 students. So we need to find the number of students that are not studying a foreign language. That's going to be 1 minus 21 over 25, which is 25 over 25 minus 21 over 25, and that's going to give us 4/25. That's the probability that a randomly selected student is not taking a foreign language. All right. Now on to the next example.
All right, our third example here, we want to find the probability with permutations or combinations. So we have each student receives a 5-digit locker combination. What is the probability of receiving a combination with all odd digits? So again, if we're thinking about this, we need to figure out how many different options we have. So if we have 5 digits and we can put any digit in there, we have 0 to 9 for each option. So really that's going to give us 10 different in each of those. That last one, 0 to 9. But that is an option of 10 for each of them. So if we find out, if we find all the possibilities, 10 times 10 times 10 times 10, or 10 to the 5th, is going to give us, well, with 5 zeros there, so 100,000 different possibilities for these locker combinations. Now, we want to know if those are all the possible outcomes. We're looking for finding one with just odd digits. So if we had 10 options to choose from, we have to think about, out of those 10 different digits, how many of those are odd? Well, in each case, we're going to have 5 options for odd numbers. We'd have 1, 3, 5, 7, 9 for each of those spots in our locker digits. So we'd have 5 options for the first number. We'd have 5 for the second, 5 for the third, 5 to the fourth, 5 to the fifth. So we have 5 to the fifth, or 5 times 5 times 5, keep going there, 5 to the fifth options. So if we want to know what 5 to the fifth options would be, that's going to be 3,125. All right, so we want to know, what's that probably going to be? It's going to be 3,125 divided by 100,000, which we could probably reduce here. So let's see, if we wanted to reduce what that's going to be, I think it's going to be 1 over 32. Let's just verify that for a second. Okay, again, which reduces to 1 over 32. So that's our probability for just getting the odd digits in our locker combination. This leads us to our second must-do. A DJ randomly selects 2 of 8 ads to play before her show. Of the 2 ads, or two of the ads, are by a local retailer. So what is the probability that she will play both of the retailer's ads before her show? So again, you want to first figure out if she has two, she's choosing two from a group of 8. How many possibilities are there in this case? And does the order matter? And then we have the only 2 of those ads are by the local retailer. So you only have one option there of what could work. So see if you can figure out what that second must do would be. Now let's get into a little geometric probability. It's going to be a form of theoretical probability determined by a ratio of lengths, areas, or volumes. So in this one, we have a figure is created by placing a rectangle inside a triangle, inside a square as shown. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded region? So we're going to need some area formulas for this case. So when we are finding the area, let's first start with the largest figure here, the square. So how do we find the area of a square? Well, it's going to be the side length squared, and our side length looks like it's 9 centimeters there. So 9 centimeters squared will be 81 centimeters squared. All right, next up, maybe we'll try the area of the triangle. Again, area of a triangle is going to be 1/2 base times height. So my base in this case, along the bottom, which is just one side of the square, my base is going to be 9. And my height of my triangle, which is going to be the same height as the side of the square, right through there, the altitude, those are equivalent, is going to also be a 9. So if I multiply that together, this is going to be 40.5 centimeters squared for our triangle. Finally, our last shape here will be the area of our rectangle. So our rectangle area formula is length times width, and our length in this case looks like it's going to be a 3, and our width, or you can call it the height, is 4. So 3 times 4, so the area of the rectangle is 12 centimeters squared. Now, we're looking for the probability that the point is inside the shaded region. So we have to figure out what is the shaded region of this figure. Well, the shaded region, the whole triangle would have been shaded, but I've taken out this rectangle. So I'll take the area of the triangle minus the area of the rectangle. So we're going to have 40.5 centimeters squared minus 12 centimeters squared. So if I subtract those two, 28.5. If I do this, let's make sure, 20. Yeah? Okay. All right. So now we want to figure out what is this probability. So the probability of the point being in the shaded region is going to be, well, how much shaded area is there? 28.5 centimeters squared. So area shaded over the total area of the square. Area total, all right, which that square encompassed all of it. So we'll say 28.5 divided by 81, which is the area of my square. So that would be where we would leave our probability in this case. So it's again 28.5 divided by 81. Okay. All right. So let's move on to experimental probability.
Okay, you can estimate the probability of an event by using data or by experiment. So for example, if a doctor states that an operation has an 80% probability of success, 80% is an estimate of probability based on similar case histories. Each repetition of an experiment is a trial. The sample space of an experiment is the set of all possible outcomes. The experimental probability of an event is the ratio of the number of times that that event occurs, which is the frequency, to the number of trials. So experimental probability is the number of times the event occurs divided by the number of trials. Experimental probability is often used to estimate theoretical probability and to make predictions. So in this example, we're finding the experimental probability. This table shows the results of a spinner experiment. Find the experimental probability. So this time, we had a spinner. There was 4 numbers on the spinner, 1, 2, 3, and 4. When we spun the spinner, the number 1 showed up 6 times, the number 2 showed up 11 times, 3 showed up 19 times, 4 showed up 14 times. So what is the experimental probability of spinning a 4? Well, that's going to be the number of times that the 4 showed up, which is 14. out of the total number of spins that we did, which if we add up 6, 11, 19, and 14, that adds up to 50. So the experimental probability would be 14 over 50, which if we want to reduce, we could write that as 7 over 25. All right, so that brings up example 5b, also a spinner experiment. This time we are finding the experimental probability of spinning a number greater than 2. So a 1 showed up 6 times, 2 showed up 11, and so on. The probability of spinning a number greater than 2 is going to be the probability that we spun a 3 or a 4, which would be 19 plus 14, divided by the total number of spins, and we had added those up, and they added up to 50. So we get 19 plus 14, which is 33 over 50. So that's our probability. That's our experimental probability that we spun a number greater than 2. And that's it for section 7.2. I hope you took good notes and did all your notes must do, and we'll see you next time.